Right now, the world's most sensitive data is locked behind standard AES-128 encryption. AES-128 is the advanced encryption standard, a globally accepted cryptographic protocol that uses a 128-bit key to scramble data into an unreadable format. Classical computers are mathematically bound to guess that key using brute force. They have to check every possible combination one by one, a mechanical process that would take modern machines billions of years to complete. But what if we stop guessing blindly? What if we place an artificial intelligence inside a quantum processor and ask it to learn the mathematical pattern of the lock? To find out, we engineered an auto-scaling quantum decryptor. The objective is to test different quantum architectures against a gauntlet of real-world cryptography. We can systematically increase the depth of a quantum neural network as the encryption gets harder.
A quantum neural network, or QNN, is a machine learning model that runs directly on quantum hardware. By scaling its depth against a strict curriculum of algorithms, we can measure if quantum AI actually has the raw potential to break military-grade encryption. Phase 1 establishes our baseline. We start with an 8-qubit dual-system architecture built in Qiskit. Qiskit is an open-source framework used to program quantum computers. This circuit uses a Pauli feature map, which translates classical data into quantum states, connected to an efficient SU2 block, a circuit template designed to train the machine learning model. This creates System 1, a shallow network. It attacks the data first, searching exclusively for simple, linear patterns to decrypt the key. We measure its success using something called friction. Friction is a mathematical score, calculated as 1.0 minus the state fidelity, that tracks the exact difference between the network's decrypted guess and the true plaintext. If that friction score stays high, it means the lock is too complex. System 1 fails and automatically triggers System 2, a much deeper network with significantly more trainable parameters. This dual-system survival mechanism is highly efficient. It conserves computing energy on easy targets and only scales up its processing power when it hits a complex algorithm. Phase 2 puts this architecture to the test against real-world cryptography, escalating from simple XOR logic up through MD5, SHA-256, and finally AES-128. MD5 and SHA-256 are widely used hashing algorithms that mathematically scramble data into a fixed-length code. Immediately, we hit a dimensional bottleneck. Real-world hashes are 256 bits wide, but our baseline quantum processor only has 8 qubits to catch that information. To fix this, we build a PCA bridge. PCA is a statistical technique that compresses large datasets by throwing out noise and keeping only the most critical mathematical patterns. As the network battles this curriculum, it logs every friction calculation, success, and failure into a BigQuery ledger. BigQuery is a cloud-based data warehouse designed to process and query massive datasets at high speed. PCA successfully forces the real-world data into the 8-qubit processor, but that compression sacrifices data resolution, leaving the network without the raw power needed to crack the highest levels of the curriculum. That brings us to Phase 3, the ultra-deep quantum decryptor. To break the hardest targets, we have to strip away the PCA compression entirely. We expand the hardware to 10 qubits and multiply the network depth to 5 distinct layers. This creates 120 individual trainable synapses, drastically expanding the model's capacity. This enables direct qubit embedding. Instead of funneling the data through a filter, we feed the raw mathematical chaos of the encryption straight into the quantum states. The workload here is brutal. To untangle AES encryption at this resolution, System 2 is forced to grind through up to 600 iterations just to chip away at the friction. This direct embedding model is the absolute most aggressive, high-resolution configuration we tested for untangling nonlinear cryptographic patterns. This chart shows the final data from our BigQuery dashboard, tracking the battle between quantum AI and the encryption curriculum. In the early levels, friction drops below the 0.20 threshold, proving the AI successfully learned the cryptographic key. But the data also shows a hard reality. Against military-grade AES, the network hits a wall. The QNN is bottlenecked by low iteration caps and the physical limits of today's quantum hardware. Despite those physical limits, the underlying architecture works. It mathematically minimizes friction in a highly directed way, cutting through a space where classical logic would just guess blindly. As quantum hardware scales up, we will be able to run this hybrid architecture over millions of iterations. And when we finally do, it holds the realistic potential to eventually unlock the encryption that secures our digital lives.